To understand what a digital signal is, we first need to understand what analog is. Now, analog signals are going to be continuous in space and time. And what that means is if I have a voltage or I have a temperature, I can have any value along these x and y axes. And in our case, the y-axis is going to be the one that we're most concerned with right now. And that's because digital signals are limited to a certain number of values along that y-axis. Probably the most common digital signal is binary, which is limited to 2 values. And what that means is that you might have that same voltage or temperature, but I'm limited now along this y-axis to only these 2 values. I can't have anything in between, anything above, or anything below. So what's the big advantage of having a digital signal over an analog signal? Well, the first one is probably noise. If I have an analog signal like this one here, and I have noise on top of that analog signal, so in fact my real signal that I'm measuring is this pink signal right here, that would be actually what I see, it's hard to figure out then what that yellow signal underneath was. In contrast, if I have a noise on my digital signal right here, I can have a lot of noise on this and still have a threshold that tells me that everything above this line is a high value, everything below it is the low value. And so that's one of the ways that a digital signal can be more robust to noise, and that's particularly important in digital communications. Another big importance of digital signals is the flexibility, because ultimately digital circuits, in contrast to analog circuits, are going to get me software. And software is going to allow me the ultimate flexibility in actually changing how my mechatronic system ultimately behaves. And then finally, manufacturing is going to be a big advantage to digital signals. Analog signals and analog circuits like resistors and capacitors that are composed of resistors and capacitors are going to take up a lot more space on a piece of silicon than the transistors that form the backbone to digital circuits. Now these digital signals and digital devices like your microcontroller and your Arduino all the way up to your smartphone and your computer are built upon the idea of these binary signals where inputs and outputs can be interpreted in one of 2 ways. I can think of things as a 1, I can think of them as high, I can think of them as true, I can think of them as on, or in contrast, I can think of things as 0 or low or false or off. And these are my digital abstractions. In contrast, if I look at the real world here, so maybe I have that same voltage, let's just pick a voltage in this case, then everything above a particular line, let's call this one V high, everything above that is going to be interpreted as this 1 high, true, or on. And I can have another line that I'm calling V low, where everything below that is going to be interpreted as this low, 0, false, or off. And that's ultimately the real world or the lab that I might see there, what I might see in the lab. Now in this binary world, I'm limited to only 2 values, 1 or 0, but I can represent more numbers than that if I combine all of these 1s and 0s into much larger words, or larger numbers. A bit is going to be a single 1 or 0. A byte, which you've no doubt heard of previously, is going to be a sequence of 8 bits all connected together. So an example of that might be 1011, 0101. And finally, because somebody was clearly hungry when they were coming up with these names, a nibble is going to be a 4-bit digital word. So a digital word is once again a sequence of bits. So in this case, a sequence of 4 bits. An example of a nibble might be 1010. Now this is going to require a little bit of a change in thinking. We're used to a base 10 system, probably because we were born with 10 fingers. And a base 10 system, if I want to represent a number like 351, I'm going to represent that by a number of digits multiplied by multiples of 10. So in this case, 3 times 10 to the 2 plus 5 times 10 to the 1 plus 1 times 10 to the 0. And in this case, the 10 here is representing my base. The 3, 5, and 1 are representing my digits. And what this tells me is a combination of m digits is going to give me 10 to the m possible numbers. If m equals 3, I can have numbers from 000 to 999, because in base 10, my digit can be anything between 0 and 9. So this is, not surprisingly, 10 to the 3 different numbers, 1,000 different numbers from 0 to 999. But what if we only had 2 fingers? We had a base 2 system instead. So if I want to represent what we think of as 6 in base 10 in base 2, now instead of multiples of 10, I'm using multiples of 2 to do the same thing. And in this case, my digits can be composed of either 0 or 1. I can't go all the way to 9 like I did with base 10. So to make 6, I'm going to have 1 times 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 2 to the 0. And so my final representation of 6 in base 2 is going to be 110. And this little subscript here is how we represent what base we're in. So 6 is in base 10, 2 means I'm in base 2. And similarly, m digits, or bits, are going to give me now 2 to the m possible numbers. So if m equals 3, instead of 10 to the 3, I'm going to have 2 to the 3, or 8 different possible combinations of numbers, all the way from 000 up to 111. If m is 8, I'm going to have 2 to the 8, right? 8 is a byte, which is 256 possible numbers. And if m equals 10, 2 to the 10 is going to be 1024. And in this case, our decimal and our binary worlds collide. This is often referred to as a kilobit, even though it's 1024 and not 1000. So if you see kilobyte somewhere, it's not exactly a multiple of 10. So finally, if I'm talking about multiple number bases, I need to know how to go back and forth from one to the other. If I'm talking about binary or base 2 and I want to go to decimal or base 10 here, I might have a number like this, 1010111111. So this is a 9-bit digital number. And in order to do this, I'm going to look at the example that I provided you previously, where I'm going to multiply each of these digits by a power of 2. So I start writing this out. 1 times 2 to the 8 plus 0 times 2 to the 7 plus 1 times 2 to the 6 plus 0 times 2 to the 5, and then I have 1s the rest of the way. So 1 times 2 to the 1 plus 1 times 2 to the 0. And if I add all of these things together, for example, this gets me 256, this gets me 64, and so on. I add all of those, I'm going to get 351 at the end. And that is my base 10 representation of this 9-bit digital number. And finally, to go the other way around, I'm going to go from decimal, base 10, to binary. And it's a little more complex to go in this direction. And to do this, I'm going to follow this algorithm here. So I'm going to start with 51 as my base 10 number, and I'm trying to represent that in binary. So I'm going to divide 51 by 2 as the first step here. I'm going to get 25.5 from that. If it has a remainder, I'm going to write 1 here, which it does. And so I'm going to take the whole number remaining and repeat that. So 25 then divided by 2 is going to get me 12.5. I have a remainder again, so I'm going to write another 1 there. I'm going to take the whole part. 12 divided by 2 is going to be 6. I have no remainder, so I write 0. 6 divided by 2 is 3. I'm going to add another 0. 3 divided by 2 is going to be 1.5. I have a remainder here, so I'm going to write 1. And then finally, 1 divided by 2 is 0.5. I have a remainder, so I'm going to write another 1. I have 0 remaining as my whole part, so I've ended the algorithm. So this number right here, 110011, is my base 2 representation of the decimal 51.